Welcome to GiulioBursiOptics, your channel for non-imaging tutorials. Today we'll talk about edge rays. Let's start from a simple imaging layout. We have a biconvex lens and a light beam reduced to the bare minimum, the rays that define the image, and the chief ray going through the lens. In this system, we get a focused image of the object in this position, and there is a magnification set by the two conjugate distances, and the image is of course inverted. In imaging optics, we are not really interested in the direction of the light beam. What we care about is the projected image of the object under examination, if we are talking, for example, about a microscope. So what changes when we move to the non-imaging board? Here we have no image to focus. Actually, the main goal is to have nothing in focus at all. Picture yourself lighting a facade with a spotlight and seeing a huge projection of the yellow square of the LED on the wall. That is exactly what we want to avoid. What is the key point then? Our source produces a certain flux, and our job as designers is to get most of that flux onto the target defined by the project, possibly in the softest and most uniform way, and, as we just said, without visible artifacts in the space. Since we are transferring flux onto a target, the most useful thing we can do is define a boundary that all of our light has to stay within, so we get the highest possible efficiency. If we find a way to keep all the light inside a given projected angular range, then, reflection and transmission losses aside, we have the guarantee of the best efficiency we can get. The way to get there is to define or to identify the edge rays. Edge rays are the outermost rays of the light distribution. So if those rays land on the border of the target, then every other ray, all the rays that lie inside those two outermost ones, will land on the target as well. Let me state this properly because it is the design rule the whole field is built on. If our optic maps the edge rays of the sources onto the edge rays of the target, then all the rays in between land inside the target. That is the edge ray principle. Two things are worth saying about that. First, it is just a sufficient condition, not a necessary one. It is not the only way to get light on the target. It is the way that gives us something we can actually design with, a construction rule, instead of a trial and error loop. Second, it is rigorous in two dimensions. In a three-dimensional rotationally symmetric system, it becomes just an approximation because the rays that never cross the axis, the skew rays. So, how do we proceed in practice? Academically, every optic lens or reflector is designed starting from a point source. There is really no other way to start. So we take a point source, and from there we draw the base optic that gives us, at least to a first approximation, the shape that we need. Here, for example, I'm looking at a reflector computed exactly that way, starting from the origin. In the real world, though, LED sources are not point sources at all. They have a spatial extension that is quite relevant compared to the dimensions that we are dealing with. Sure, you can take a 20mm lens, and if you put it inside a reflector 1 meter wide, its size is irrelevant. The problem is that, for obvious packaging reasons, we often combine sources in the order of 6 to 9mm with lenses in the order of 30, 50mm. We are not even at a factor of 10. We are at 4 to 5 times when you are lucky. So you can see that relative size effects carry a lot of weight in the design. So let's run the simulation for two different reflectors. One designed with only the point source in mind. and the other where I tried a little compensation for the extended source. Here we have two ray fans, one centered in the origin and the other offset by 4 mm from the center, which represents the border of a medium-sized LED. If you look at the results of the simulation, we see that in the first case, the one with the point source reflector, rays are all over the place, especially the one coming from the offset source in this region are completely off the target. Now, if we trace the other case, we see that all the rays are more concentrated and every one of them hits inside the target. Non-imaging optics deals with extended sources. It always works in a compromise. So we have to look for the best curve, the one that is the compromise between the size of the source and the target we want to hit. The edge will not be sharp, we will have a certain gradient, and we will have some stray light. Stray light can produce glare, which is the worst thing of all. Still, our job as optical designers is exactly this, finding compromise solution between the constraint of the source choice, and the constraints of the target. Now let's take a more complex case. Not a simple reflector, but a lens that splits the beam. A lens of this kind, a TR lens, splits the beam between a central zone and the external zone where the TR happens. How do we define the edge rays in this situation, since the beam is clearly split into several parts? Here the definition becomes more flexible, but we can still analyze the edge rays for each of the zones the beam is split into. So we look at what happens in the central zone, for instance by simulating it, creating these ray fans at different positions, and then we look separately at what happens in the outer part, where the beam is reflective of the walls. Each of the two distributions will have its own edge rays covering a certain angle of the target. And we add the faceting on the lens. Because we want more mixing, the situation gets even more complicated. In that case as well, we have to build distributions that stay controllable as far as possible, and analyze the edge rays produced by the different facets. This is clearly a long and complex process, which is why designing a complex lens takes a considerable amount of time. So, as a final note, keep in mind what we discussed in the previous video about wet and dew. The edge rays tell you where to send the boundary of the beam, but they will never tell you how to shrink it. And remember, do not try to beat the wet and dew limit, because that will always be the hard limit imposed by the laws of physics. Thank you and see you in the next video.